This is Andy Stark, Intercomparison of Cloud Filling Algorithms for Marine Satellite Data.
Hi everyone, my name is Andy Stark. I'm an EI postdoc based at Le Mont Doherty Earth Observatory. For my talk today I have to thank a large number of co-authors. And another part of the prelude is a warning that I give out whenever I give a talk to people who I don't know that well, which is that I was actually a computer science undergrad, and somehow that has instilled me with a lifelong distrust of anything that comes out of a computer. And this really shows in the kind of way that I think about these problems. So my talk is going to be about cloud filling algorithms for marine satellite data. And as for terrestrial systems, satellite remote sensing has really changed our understanding of the global spatial ecology and biogeography of the oceans. There are a large number of biological and physical variables that we can measure from space, and one of the most important ones in the marine realm, and the one that I'm going to talk about today, are chlorophyll A concentrations. Chlorophyll A is the proxy for phytoplankton biomass. Phytoplankton are the source of the marine food web, the base of the marine food web, and the foundation of the biological carbon pump in the ocean, and therefore it is extremely important to be able to monitor what happens to phytoplankton globally. So how does all this work? This image shows a large plankton bloom in the Atlantic. And it's a bit more complicated than that, but basically the greener the water looks from space, the more phytoplankton is in the water. And it's this variation in ocean color that allows us to quantitatively estimate how much chlorophyll A there is, and based on that to estimate related variables like biomass, primary production, and carbon uptake. There is, however, a major problem with ocean color observations from space, and that problem is clouds. Large parts of the image that you're looking at right now is covered by clouds, but overall this is an exceptionally clear image. On average, about 2/3 of the oceans are covered by clouds at a given time, and that's problematic because things in the ocean can change very quickly. And the satellites that are typically used for broad-scale monitoring of marine phenomena have revisit times of about 2 days. So if then they visit after 2 days, and again after 2 days, and again after 2 days, and it's cloudy, most of the time we can go very long time without getting any valid observations. In fact, in some extremely cloudy areas with long dark winters and sea ice, we might get as little as 10 or fewer looks at the ocean surface in a given year. The second problem related to cloud cover, besides not being able to see at regular intervals what's going on, is that clouds are not distributed evenly. For example, in many coastal waters, there is systematically less cloud cover than in many offshore waters, but coastal waters also tend to have higher phytoplankton concentrations. So if we don't correct for the fact that some locations get systematically more frequently observed than others, our estimates of regional primary productivity, regional biomass, and so on might be off. And for that reason, different researchers have proposed so-called cloud filling algorithms, which are basically just models that try to fill in the gaps in satellite images caused by clouds with reasonable estimates of chlorophyll or whatever variable we're actually looking at. And the papers proposing these algorithms tend to present evidence according to which their algorithm works particularly well, little surprisingly, but so far nobody has been quantifying how well the algorithms actually work or compared their performance in a sound quantitative way. So in the project that I am presenting today, I aim to answer 3 related research questions. First, how accurately can existing and various new cloud filling algorithms predict chlorophyll concentrations under the clouds? Second, which of these algorithms have the best ratios of performance, computational cost, and effort of implementation? And what I'm aiming at with this question is really that some of these algorithms are really complicated and time-consuming to work with, and it might not always be worth to go through the trouble for if there are only minor gains in performance. And third, that is more aimed at people who plan to develop new cloud filling algorithms. What are the shared properties of the best performing algorithms? So in order to answer these questions, I tested how well 8 algorithms could fill gaps in MODIS and CWIP's chlorophyll A concentration data. These are satellite instruments, and I looked at 3 study areas: the Beaufort Sea, the Chukchi Sea, and the tropical Atlantic, and more areas are to come in the future. Here's a list of the 8 algorithms that I tested so far. There are others worth testing, certainly, and those highlighted in orange are new in the sense of that they are general purpose algorithms, but they have not been applied to cloud filling before. And I won't have the time to work you through all of the individual algorithms, but very roughly they can be put into 2 categories: interpolation algorithms and regression algorithms. So interpolation algorithms make use of the temporal and spatial structure of the chlorophyll data or whatever variable we're interested in themselves. So they predict chlorophyll under the clouds based on adjacent cloud-free locations, and by adjacent I mean adjacent in space, adjacent in time, or both. In contrast, statistical learning or regression algorithms take a variety of variables that are typically related to the processes that drive phytoplankton dynamics in the ocean, such as sea surface temperatures and sea level anomalies, and try to predict chlorophyll concentrations under the clouds based on those data. Although, in fact, these are very flexible approaches, and they can, what I call, include interpolation features, which basically means they can also be set up in a way such that they mimic interpolation, in addition to incorporating all these other biological and physical variables. I tested each of the 8 algorithms in 3 steps. First, for each of the study areas, I searched for relatively cloud-free images, which I defined as images where more than 90% of pixels were visible. So this example is from the tropical Atlantic, and I forgot to tell you before, I worked on 8-day composite data, which means that the images that I'll be showing you here now are combining several images from several satellite overpasses over the course of 8 days already. And just to give you an idea of the scope of the cloud problem, depending on the study area, I searched through 20 years of data, and even combining several images together, I could find only between 10 and 50 in 20 years for each area where more than 90% was visible. Once I had identified a set of relatively cloud-free images in each study area, I put clouds from different images on top. And this process, there were a couple of hundred cloud masks in each study area, so depending on the study area, this process gave me between 750 and 9,000 different situations to test the algorithms on. And then I took the images with the transplanted clouds and applied the algorithms to reconstruct the original images. And in this example, this is a reconstruction by means of a statistical learning method called a random forest. Just from looking at it, it's not perfect, but it looks relatively good. And this is pretty much the point where everything that I have seen in the literature so far stops. Take an example, look at it. It looks okay. It must be a good algorithm. So, as I mentioned before, I did this several hundreds or thousands of times in each study area and calculated 2 error estimates over it. 2 error estimates. Comparing the original and the reconstructed images, I first calculated the average root mean squared error of all pixels under the transplanted clouds. So that's a measure of how accurately the cloud filling algorithm could reconstruct chlorophyll concentrations in particular locations. But I also looked at the differences between the study region's mean chlorophyll concentration according to the original images and according to the constructed images. And that's a measure of how much clouds affect and how much these algorithms can improve regional averages and time series of regional averages. And it's that error in the spatial mean that I want to focus on during the rest of my talk, although the results for the per pixel predictions were not fundamentally different. So this bar chart shows the expected root mean squared errors of the different algorithms. And because the bars represent errors, a shorter bar means that the algorithm is better in this particular situation. The bar on top is the error of the spatial mean calculated without any prior cloud filling. And we don't have the time to look at individual algorithms again, but I have highlighted the 3 best performing algorithms in each study area. And I want to provide you with 2 main takeaways from this chart. The first one is that all of the best performing algorithms perform some kind of interpolation in space or in time, or most commonly in both space and time. And the second major takeaway is that by means of the best algorithms, we can reduce the error when estimating regional means by, depending on the study area, between 50 and 80%. This plot shows the same errors just summarized in a different way and with a little bit more detail, and only for the tropical Atlantic study area. So here the vertical axis is the root mean squared error of the spatial mean, and the horizontal axis is cloud cover ranging from 0 to 100%. So as we move right in this chart, we move from completely clear skies to complete cloud cover. And the first thing we notice is that, as expected, as it gets more cloudy, the errors actually go up. So, yeah. The thick white line in the middle is the error of the spatial mean estimated without any cloud filling. And the dashed white line near the bottom is the best error that we can theoretically expect to achieve. That's the part of the error that's not related to clouds as such, but simply to reduction of the sample size as we have fewer and fewer pixels to calculate the mean from. And as you can see, there are several algorithms that are all near the bottom and hard to distinguish except at extremely high levels of cloud cover. This includes 2 of the regression algorithms, random forest and ridge regression, but only if they included interpolation features. As a test, I tried to run these algorithms without doing any interpolation, and that gave us, for example, the dashed yellow line that is much better, much worse than not doing any correction at all. In summary, I found that the different algorithms showed quite a wide range of performance, but that some algorithms performed consistently better than others. Overall, kriging and statistical learning approaches work best, in most situations that is, but they are difficult to use and take a lot of computation time when applied to large data sets. So an algorithm that I did not mention before, that worked relatively well in most situations and is much easier and faster to use, is called DIN-EOF, Data Interpolating Empirical Orthogonal Functions. It's one of the most widely used ones, and it would actually also be my recommendation for situations where you don't need to have the absolute highest accuracy. And the best performing algorithms focused on smart interpolation from visible parts of the study area and from past and future images. So even though at extremely high levels of cloud cover, it's actually helpful to feed in additional data on biological and physical conditions in the ocean into the models, in the vast majority of situations, what really matters is to make the best possible use of observations taken in different places and times close by when there were no clouds. So thank you very much for your attention. I look forward to answering your questions.
Yeah.
Variability and what algorithms work better in different regions? Have you started thinking about why physically, or what was specific about these regions that matches better with some algorithms, or is it the fact that we haven't found the best algorithm that would work everywhere?
Yes, good observation. That's absolutely right. And I haven't been unpacking all of the variation in performance between the different algorithms in detail. But for example, there are some regions that have a very clear gradient or very broad scale regional patterns that do not change quickly in time. So in this case, temporal interpolation works really well. If things change around in a region regularly all the time, then temp interpolation in time is not going to work that well. So this is one of the, basically spatial and temporal variability within the different regions is one of the main things that drive which algorithms work well.
Thank you. I was actually proceeding in the same line of questioning. I was wondering how the result would depend on the variable you are reconstructing. For example, you started doing that with a rather complicated field with small scale and fast, small scale short-term variability like chlorophyll. With sea surface temperature, it perhaps would be easier and perhaps you would get a more clear picture.
Yes, it would probably be different for sea surface temperature because chlorophyll concentrations tend to be more patchy and less gradually changing. So you're absolutely right on this. My only concern is that I really don't want to go through all this work with another variable again.
Right, but you know, there is a wisdom in doing small steps, and perhaps just to make some trying to be useful, I would suggest that you could try to experiment with a fixed, small, simple, say, rectangular area, and a field which would be having varying synthetic fields with simple statistical characteristic like spatial temporal variability, which you could vary and see how it would change the results in terms of methods. Perhaps that would be the way to get a clear picture.
Yeah, that could be my next project. Thank you.
I have a question. I understand that you take as a reference, as the true value, these 8 days free clouds window. I was wondering if this window can affect in some way the kind of vegetation that at the end you are going to have. So I was wondering if there is possible to have like a bottom approach that you can measure under cloud and then compare with your metrics having clouds. I don't know.
You mean measuring in the field under the cloud?
Yes. This is not my field, so
I don't have that kind of money, but yes. So one of the reasons I go about it in this way is that one of the major challenges in generally applying regression modeling, artificial intelligence, machine learning approaches, any algorithms that need labeled data, one of the challenges for them in the marine realm is that we have so few in situ data. And this is basically one attempt to get around that limitation and get basically 1 million pixels to look at when I train my models, as opposed to dealing with 150 co-located observations that are really clustered in space and not even independent. So.
And what is the criteria to decide this 8 days window? Why not 20 or 5? Or I don't know, what is the...
So the 8-day window, first of all, it's a standard data product makes it easier for me, also makes it much more widely used. And if we are interested in seeing to what extent, and I didn't talk about this will be a part of the paper coming out of this, to what extent we can actually see short-term oceanographic phenomena. If we're averaging over a month, we're not going to see them anyway. So looking at daily images, we would have a lot more cloud cover. There might not be anything we can do about it. One thing that I'm planning to do is to look at regions that have less cloud cover overall, and look at daily data as opposed to 8-day composites from these regions.
And why 8?
Why 8?
What's magic about 8?
I can download the 8-day composites as opposed to doing it myself, and other people can download them too. So it's just a standard, and I don't know if Ajit knows why it's 8 days, not 7 or 9, but probably just somebody needed to make a decision.
And that's roughly the average lifetime of the cloud, right?
Is it?
Yeah.
I had no idea.
I think that would do the feasibility have qualified scale quantity.
I think the average residence time of a molecule of water in the cloud is 8 days.
Okay.
I'd just like a better reason than the one you gave for 8 days.
I didn't invent it, so I'll try to find out who's the right person to ask.
Okay. Well, other questions for any of the previous speakers? I think I suppressed a few for the first speaker.
Questions for Megan? Thank you very much for a very engaging presentation. You clearly enjoy what you study. Your president is trying to pull out the Paris Agreement, but the endeavors that you have in New York are quite laudable in terms of sustainability. One notable one is the schools, the 1,100 schools in New York. The program that started, I think, in 2010, where they appointed coordinators. So I know you said that you're very early in the stage of your research, but it'd be a very good idea to link up what you're doing on the streets into the schools, because the schools are actually struggling to get some sort of structure for the coordinators. So what you're doing right now is very interesting. It could be extended to that. I attended some focus groups regarding that same subject, and they do need some structured help. I think what you're doing is really, really good. Did you ever consider permaculture at all? Yeah, for the trees.
Thank you. So one, let me talk to you a little more afterwards about the school connection. As far as permaculture goes, one of my leading questions is to understand if anyone is using permaculture methods in pits. Once we start interviewing, we'll be able to answer that question, because there are pits that to me look like, I can't tell if they're untended or if they're permaculture style pits. And once we talk to people and can determine the intentionality there, we'll be able to answer that a little better. I certainly think permaculture has a lot to offer as a design solution in the future.
Question for Megan also. Thank you. Great study. Curious, you mentioned that there were some surveys saying that folks don't like bioswales. What were the reasons that they mentioned? Do they understand what bioswales are? Are there other terms that could be used to explain it? Same question for stormwater retention. Do people understand how it works? Is it maybe just a lot of education?
That's a great question. When it comes to the reception of bioswales, they're very new in the city. They've all been installed in the last couple of years. I want to say 2, 3, maybe. So we don't have any formal information on that. It's mostly sort of anecdotal, 311 call data, what other organizations are experiencing in terms of feedback, and so we don't know. There's not an actual formal survey on that. Education around the bioswales has been pretty limited, and that has a lot to do with how the rollout has played out on the part of the city, which I'm happy to explain in greater detail later. But there hasn't been a lot of education around them, and that is one of the things that is concerning and that we want to look at in the future.
Megan, I would like to, I enjoyed your presentation a lot, and I want to join with Alison's presentation as well. And have you thinking in linking like participatory process in this grow of trees, and what is the effect? I was thinking, for instance, in voluntary or community gardening, and what is the effect on the perception and the involvement of the communities.
So, to understand your question, you were wondering about community gardens? Oh, yeah. Okay. Yeah, I follow. So with the bioswales, it has not been participatory. And that is something that is being addressed by, or a couple organizations in the city are attempting to address, and that's something that we are also looking at. The interesting thing about the tree pits is that the tree pits themselves are not something that communities have input on, but what goes into them is. And so it's highly participatory once the pit and the tree are there. And that's certainly something that we want to investigate, because one of our sort of leading ideas here is that when people have control about what gets planted and how it is tended, they have a greater sense of ownership over it. And I think the example of community gardens also supports that there's people like to be able to control their built environment as much as possible in that way.
This is the, sorry. Well, thank you all for attending this afternoon. Very pleased to see so many of you, including one member of the admissions committee for the program. Thanks for coming. What you've seen today is a sample, a small sample of the postdocs in our program. What you will have recognized is the uniform excellence of the presenters, and also the non-uniform subject matter of their work. And that's a hallmark of what we try to do. We don't have a specific theme other than there should be some salience to the big issues of sustainable development somehow. We're in the process of selecting a new group of postdocs. We usually get 6 to 8 a year, something like that, for a 2-year program. So if you're nearing the end of your PhD and you're thinking of a postdoc, I'm the person to ask about it, and I'll be here for a few minutes, or you can email me. So once again, thank you all for coming, and see you in the spring.